Hello and welcome. My name is Alan, and today I'll be reading more Ideas and Opinions, Albert Einstein. Today we're going to read a piece about Johannes Kepler. Blurb reads, on the occasion of the 300th anniversary of Kepler's death, and was published in the Frankfurter Zeitung, Germany, November the 9th, 1930. In anxious and uncertain times like ours, when it is difficult to find pleasure in humanity and the course of human affairs, and it is particularly consoling to think of such a supreme and quiet man as Kepler. Kepler lived in an age in which the reign of law in nature was as yet by no means certain. How great must his faith in the existence of natural law have been to give him the strength to devote decades of hard and patient work to the empirical investigation of planetary motion and the mathematical laws of that motion, entirely on his own, supported by no one and understood by very few. If we would honor his memory fittingly, we must get as clear a picture as we can of his problem and the stages of its solution. Copernicus had opened the eyes of the most intelligent to the fact that the best way to get a clear grasp of the apparent movements of the planets in the heavens was to regard them as movements round the sun conceived as stationary. If the planets moved uniformly in a circle around the sun, it would have been comparatively easy to discover how these movements must look from the Earth. Since, however, the phenomena to be dealt with were much more complicated than that, the task was far harder. First of all, these movements had to be determined empirically from the dimensions of Tycho Brahe. Only then did it become possible to think about discovering the general laws which these movements satisfy. To grasp how difficult a business it was to even to determine the actual movements around the sun, one has to realize the following. One can never see where a planet really is at any given moment, but only in what direction it can be seen just then from the Earth, which is itself moving in an unknown manner around the sun. The difficulties thus seemed practically insurmountable. Kepler had to discover a way of bringing order into this chaos. To start with, he saw that it was necessary first to try to find out about the motion of the Earth itself. This would simply have been impossible if there existed only the sun, the Earth, and the fixed stars, but no other planets. For in that case, one could ascertain nothing empirically except how the direction of the straight sun-Earth line changes in the course of the year, apparent movement of the sun with reference to the fixed stars. In this way, it was possible to discover that the sun-Earth direction all lay in a plane stationary with reference to the fixed stars, at least according to the accuracy of observation achieved in those days. when there were no telescopes. By this means, it would also be ascertained in what manner the line Sun-Earth revolves around the Sun. It turned out that the angular velocity of this motion varied in a regular way in the course of the year, but this was not of much use, as it was still not known how the distance from the Earth to the Sun alters in the course of a year. Only when these changes were known could the real shape of the Earth's orbit and the manner in which it is described be ascertained. Kepler found a marvelous way out of this dilemma. To begin with, it followed from observations of the Sun that the apparent path of the Sun against the background of the fixed stars differed in speed at different times of the year, but that the angular velocity of this movement was always the same at the same time of the astronomical year, and therefore that the speed of rotation of the straight line Earth-Sun was always the same when it pointed to the same region of the fixed stars. It was thus legitimate to suppose that Earth's orbit was closed, described by the Earth in the same way every year, which was by no means obvious a priori. For the adherents of the Copenhagen system, it was thus as good as certain that this must also apply to the orbits of the rest of the planets. This certainly made things easier. But how to ascertain the real shape of the Earth's orbit? Imagine a brightly shining lantern M somewhere in the plane of the orbit. Assume we know that this lantern remains permanently in its place and thus forms a kind of fixed triangulation point for determining the Earth's orbit. A point which the inhabitants of the Earth can take a sight on at any time of year. Let this lantern M be further away from the Sun than the Earth. With the help of such a lantern, it is possible to determine the Earth's orbit in the following way. First of all, in every year there comes a moment when the Earth E lies exactly on the line joining the Sun S and the lantern M. If at this moment we look from the Earth E at the lantern M, our line of sight will coincide with the line SM, Sun Lantern. Suppose the latter to be marked in the heavens. Now imagine the Earth in a different position and at a different time. Since the Sun, S, and the lantern M can both be seen from the Earth, the angle at E in the triangle SEM is known, but we also know the direction of SE in relation to the fixed stars through the direct solar observations, while the direction of the line SM in relation to the fixed stars has previously been ascertained once for all. In the triangle SEM, we also know the triangle at S. Therefore, with the base SM arbitrarily laid down on a sheet of paper, we can, in virtue of our knowledge of the angles at E and S, construct the triangle SEM. We might do this at frequent intervals during the year. Each time we should get on our piece of paper a position of the Earth E with a date attached to it and a certain position in relation to the permanently fixed base SM. The Earth's orbit would thereby be empirically determined, apart from its absolute size, of course. But you will say, where did Kepler get his lantern M? His genius and nature, benevolent in this case, gave it to him. There was, for example, the planet Mars and the length of the Martian year, i.e., one rotation of Mars around the Sun, was known. At one point, it may happen that the Sun, the Earth, and Mars lie very nearly on a straight line. This position of Mars regularly occurs after 1, 2, etc. Martian years, as Mars moves in a closed orbit. At these known moments, therefore, SM always presents the same base, while the Earth is always at a different point in its orbit. The observations of the Sun and Mars at these moments thus constitute a means of determining the true orbit of the Earth, as Mars then plays the part of our imaginary lantern. Thus it was that Kepler discovered the true shape of the Earth's orbit and the way in which the Earth describes it. And we who come after, Europeans, Germans, or even Swabians, may well admire and honor him for it. Now that the Earth's orbit has been empirically determined, the true position and length of the line SE at any moment was known, and it was not so terribly difficult for Kepler to calculate the orbit and motions of the rest of the planets, too, from observations, at least in principle. It was nevertheless an immense task, especially considering the state of mathematics at the time. Now came the second and no less arduous part of Kepler's life work. The orbits were empirically known, but their laws had to be guessed from the empirical data. First, he had to make a guess at the mathematical nature of the curve described by the orbit, and then try it out on a vast assemblage of figures. If it did not fit, another hypothesis had to be devised and again was tested. After tremendous search, the conjecture that the orbit was an ellipse with the Sun at one of its foci was found to fit the facts. Kepler also discovered the law governing the variation in speed during one revolution, which in that the line Sun-planet sweeps out equal areas in equal periods of time. Finally, he discovered that the squares of the periods of revolution around the Sun vary as the cubes of the major axes of the ellipses around the Sun vary axes of the ellipses. Our admiration for this splendid man is accompanied by another feeling of admiration and reverence, the object of which is no man but the mysterious harmony of nature into which we were born. The ancients already devised the lines exhibiting the simplest conceivable form of regularity among these, next to the straight line and the circle. The most important were the ellipse and the hyperbola. We see the last two embodied, at least very nearly so, in the orbits of the heavenly bodies. It seems that the human mind has first to construct forms independently before we can find them in things. Kepler's marvelous achievement in a particularly fine example of the truth that knowledge cannot spring from experience alone, but only from the comparison of the inventions of the intellect with observed fact. So yeah, Einstein talking about Johannes Kepler and the contribution he made to the sciences, especially in regards to our understanding of the planets. Setting not only the idea in motion that mainly that the planets rotated in an ellipses, and that it was also a closed orbit, so the same path, thus never varying, which could be horribly terrifying if planets were to vary on their orbits. You could see some planetary collisions. Kepler himself is his name is given to, I think it's a telescope, the Kepler Space Telescope. But yeah, as always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.